Okay, the background of this hypothesis test is we've asked a bunch of children to draw life-size pictures of nickels, and we want to compare do maybe children in a lower income group draw a diameter that's we're looking at that's greater. Here we're looking at a greater value than the 22.21 millimeters, which is going to be our mu. We're going to assume that the mean of the population is 22.21, that the average diameter of a nickel when told to draw a life-size picture of a nickel, without, just from memory or whatnot, is they draw a circle that is has a diameter of 21.21 millimeters for all children, and we've got a group of children that are lower income, and we're wondering if there's a significant difference between the diameter they draw, if their sample, their picture has a diameter that's significantly larger than the rest of the population. And we assume that we know what the standard deviation of the population is. The standard deviation of all nickels drawn by all kids is 0.48325 millimeters. Okay, and so the idea is we're going to assume that that what we have is we want to look at, do we just have sampling variance, sampling variation here, or what's the probability that we're looking at sampling variation? The difference between the sample mean and the population mean, what's the probability that that's just random chance? And so if we work off the assumption, our null hypothesis would be that the mean drawn by the lower income kids is the same as the mean drawn by everyone else, and we're testing it against the hypothesis that the mean is actually larger than 21.21, that the mean of this lower income group of children is greater than the diameter drawn by everyone else. That it's a significant difference, that it's more than just random chance. So we want to look at what's the probability that it's random chance. And so what we're trying to do is trying to come up with, now what's the probability that my x bar ends up at 22.675 or more if the mean is really 21.21 millimeters. What's the probability that I get something value there? And that's our p. Our p-value is that probability. And so we're going to start by calculating our test statistic. In this case, because I know the population standard deviation, it's going to be a z-score. And I'm going to take my observation, 22.675, minus the mean, 21.21, and divide it by the standard deviation of our sampling distribution, which would be 48325 over the square root of 40, because we're looking at how far is the sample mean. We're looking at the distribution of sample means from our population. And so if we calculate that real quick, that's a 40 down there. That doesn't look like a 40 so much, but that is a 40. All right, so if we calculate that real quick, let me hop over to my calculator here. I have, oh shoot, I shouldn't have done that. 22.675. 22.675 minus 21.21 divided by, and then this has got to be in a set of parentheses, 2. It was 4.8325. 4.8325 divided by the square root of 40, and then 2 parentheses to close that off, and I get a z-score here of 1.973, 1.9173, or 1.92. Let's just round to 1.92. That's how we'd have to do things if we're using the table in the textbook. But then what I want to do is then find the probability, my p-value is going to be the probability that I end up in this upper tail here, and the probability of that happening I can get from my normal distribution. And I want to go from this 1.91, 1.92. Let's do 1.91735. Let's just be accurate. To infinity, and come up and see what that value is in there. So that's going to give us my p-value. That's the probability that I will end up with a sample mean of 22.675 if the population mean is really 21.21. And so let's go to my calculator. Whoops, I don't know what I hit there. There we are. I want to go to distribution, normal CDF, and I want to go from that previous answer to infinity. So we'll put in a few 9s there. All right. And again, if your calculator is asking you for a mean and standard deviation, and you've calculated a z-score like this, then you want to put in the mean is 0 and the standard deviation is 1. When we convert to a z-score, we've converted to the standard normal distribution, where the mean is 0 and the standard deviation of 1. And I get a p-value here of 0.276. We'll call it 0.276. Or 0.0276. 0.0276, or 2.76%. So I've only got a 2.76% chance of getting a sample with a mean of 22.625 if the population mean is really 21.21. So it's a really unlikely. I should not be seeing a mean like this if the a mean that big. It's unlikely. It's a small chance, 2 3/4, 2% chance that I can get a sample with a mean of 2.675 if the mean is really 21.1. And so what I would do, especially based on our significance level of alpha, is reject the null hypothesis. And we get that our sample suggests that the true mean for low-income students or lower-income students is greater than 21.21 millimeters. Okay, so we get a nice statement there, rejecting the null hypothesis. Our p-value here of 2.76% is small. It's smaller than our significance level that we were given of 5%. We're far enough away that we've got less than a 5% chance of getting a sample with a mean of 22.675 if the true population mean is 21.21, and so we're going to choose to reject the null hypothesis.